So let's do some sample calculations to show you where all this comes from. Okay. So here's a couple problems. I'm only going to calculate a few parts of this. So calculate the pH of a 0.1, 0.01, and 0.001 molar solution using H+. Okay, great. Well, hopefully this is a nice stroll down memory lane. pH is the negative log of, I'll just do the 0.1 example, and I don't even need to throw that on my calculator. I know that's going to be 1.00. Okay? So now, what if we do it in terms of, oh, and excuse me, because, this is log sig fig rules. Because I have 3 decimals in my log, is that how that works? Yes, I have 3 significant figures in my log, 1, 2, 3, so I get 3 decimal places, 1.000. Okay, so I'm just going to do that same one using the activity calculation. Okay, and so first I have to calculate the ionic strength. Okay, and so this is using H+. So we'll assume that this was from HCl just to make life easier. So we have H+ and Cl-. An interesting case would arise if we did this with sulfuric acid, if we had the -2, the divalent sulfate ion. And I'll show you that in a moment. Okay, so this is going to be ionic strength equals 1/2. And now I have to sum up all of the charges. So that's going to be 1/2 times Z times the ratio of molarities. I'm going to use the ratio of molarities, but it's going to be a very similar calculation. So that's going to be +1 squared times 0.100 divided by 1 plus -1 squared times 0.100 divided by 1. And when I sum all this up, hopefully you can see what the number is going to be, but I'll do it just for consistency. So +1 squared is 1 times 0.1 divided by 1 is 0.1. So let's just write that out. 1/2 times 0.100. Okay, and then -1 squared gives me +1 times 0.1 divided by 1 is 0.100. And 0.1 plus 0.1 times 1/2 is 0.100. Okay, so why did we even have to do that calculation? Because if we had a divalent ion, it would change the result, right? If we had something that was -2, or if we had something that was +2 or even +3 or +4, it would really change this ionic strength. So therein lies one of the big rubs in ionic strength is as you have, in excess of monovalent cations or anions, ionic strength really changes significantly. Okay. So now what we have to do is calculate the actual activity coefficient. Okay, so that goes as the following. Log of gamma equals -0.509. And of course, this is now the absolute value of 0.1, the absolute value of +1 times -1, which once again, you can see that that's not going to change this result. But if it were a divalent cation, it would be a significant difference. And now that's times the square root of 0.100, okay? And this is now all divided by 1 plus the square root of 0.100, okay? And so let's do that. So that's going to be, 0.1 square root times 0.509 negative, okay? And so I'm just going to collect this up so I get it all right. So the top half I get to be negative 0. Let's say 161 with the 3 sig figs there in the decimal. Okay, divided by 1 plus the square root of 0.100. Okay. So let's see, 0.1 square root plus 1. Okay, and so now I need to divide that Okay, great. And so I get that I'll write that over here. I get that the log of gamma equals negative 0.122, okay? So gamma equals 10 raised to the negative 1.22. So we can see that's going to be less than 1, which it should be, all right? And so let's do that. So I get this now to be 0.755. Okay, so if gamma for H plus equals 0.755, how do we calculate the pH of that now? Well, let's go back. We remind ourselves that the activity is gamma times the concentration, and then the pH will be the negative log of the activity. Okay, so now I can say the activity of H plus is going to be 0.55 times the 0.100 mole per liter. Okay. And so technically we drop out the units because really this is, it's divided by standard activity. So we don't worry about units and activity. We drop the units, okay? So that's 0.0755. And now if I do pH as the negative log of the activity, you can see this is going to be different than my 1.000, right? Okay, so let's take the log of that. So I get this to be, let's see here, 1.122. So that's significantly different than had we used concentration. I would definitely say that's significantly different because remember, this is a pH measurement. It's a log-based measurement, right? So if you're off by 0.1 in the pH, that's fairly significant. So now I didn't do this for the 0.01 and the 0.001, but what ends up happening, because these are more dilute, the calculation of pH for activity versus concentration for those more dilute examples gets better. Okay, so that's why I chose to only do this 1.0 example, because that has the biggest difference. All right. However, as you approach, like, so we know this is, a pH of 1, and this is a pH of 2, and this is a pH of 3. So as you get to those pHs, you see less and less differences, so less error if you use concentration-based pH versus activity-based pH. But what's important to note, and I'm not going to go into this again for the limit of time, but I know that your analytical chemistry professors are excellent when it comes to teaching you about probes. So as it turns out, what a pH probe is actually measuring is this. This is what actually gets measured. It measures the ionic activity. So it's basically measuring some ratio. It's measuring the activity of H plus ions to some reference point, which is why you calibrate that pH meter, okay? And also, right, I just did this for monovalent cations, like I mentioned. Had we done this for divalent cations, there's a real significant difference. I didn't put a figure in here, but there's a figure in Atkins that shows you really well how, if you start comparing like sodium chloride to magnesium chloride to magnesium sulfate, you get really significant differences, right? Okay, folks, so I think that's a pretty good amount of lecturing on activity. I'll do one more lecture on equilibrium after this, which will be more or less a review. I might have to do 2 videos for equilibrium, but we shall see. Okay, I'll see you in the next one.